In this deck, we focus on one of the most tightly coupled decision problems on the seaside of a container terminal: berth allocation and quay crane allocation. Berth allocation decides where and when each arriving vessel is placed along the quay. Quay crane allocation decides how many cranes are assigned to each vessel while it is being worked. These decisions cannot be separated cleanly. If you give a vessel a berth position and time, but do not have cranes available in that location and window, the plan fails. And if you allocate cranes without considering when and where the vessel is berthed, you can create interference, crane crossing conflicts, and unrealistic schedules. The goal is to minimize vessel turnaround cost while keeping berth and crane resources productive. The scenario is Port Harmony, a major container terminal handling over 500 vessel calls per month. The quay wall is 1,200 meters long and equipped with 15 ship-to-shore cranes. The port manager, Sarah Chen, must coordinate berth assignments with crane allocations every day. Vessels range from 150-meter feeder ships to 400-meter ultra-large container vessels. A typical day includes a 300-meter vessel needing 800 container moves that could be served by 2 to 5 cranes, and a 200-meter feeder needing 200 moves, but arriving during peak hours when cranes are constrained. Suboptimal choices cascade into delays and higher cost. We solve the integrated berth and crane allocation problem using multiple tiers. Tier 1 provides a mixed integer programming formulation that captures both spatial berth constraints and crane assignment constraints. Tier 2 uses a priority-based constructive heuristic for fast, practical decisions. Tier 3 applies particle swarm optimization to search for better integrated schedules. Tier 4 uses Dueling deep queue network reinforcement learning to learn policies that generalize across arrival patterns. Tier 5 embeds the logic in an integrated digital twin for rolling horizon re-optimization and disruption response. Tier 7 adds a human and artificial intelligence symbiotic partnership. Tier 9 introduces quantum annealing via a quadratic, unconstrained binary optimization framing. Tier 1 models berthing positions, service start times, service finish times, and crane assignment decisions as decision variables. The objective is to minimize cost-weighted vessel turnaround time, meaning finish time minus arrival time, scaled by a vessel cost rate. The value of the formulation is completeness. It makes explicit that the quay has finite length. Vessels cannot overlap in space, vessels cannot start before they arrive, and finish time depends on workload divided by effective crane productivity. Effective productivity is reduced by interference when multiple cranes work too close together. This slide defines the core sets: a set of vessels, a set of quay cranes, and a set of discrete time periods. Operationally, sets provide the indexing structure. They ensure that every berth position, every crane assignment, and every time constraint is tied to a specific vessel and a specific window in the plan. Parameters include each vessel's arrival time, length, and workload. The quay has a total length. Crane productivity rates represent how fast each crane can process a given vessel. The model also includes an interference factor that reduces productivity as more cranes are assigned. Finally, the cost per unit time for each vessel expresses the business impact of delay. A high-cost vessel should be prioritized differently than a low-cost vessel. Decision variables include the berthing position of each vessel and the start and finish times of service. You also decide whether each crane is assigned to each vessel. The model also uses a variable that represents whether two vessels are both at berth during the same time period, which is useful for enforcing non-overlap and conflict logic. The objective minimizes total vessel turnaround cost. Turnaround is the time from arrival until completion of service. Operationally, this captures both waiting and service. A vessel that arrives but cannot start because the berth is full contributes waiting cost. A vessel that starts but receives too few cranes contributes long service time. The objective pushes the plan to reduce both. This constraint ensures that each vessel fits within the quay. A vessel's berthing position plus its length must be within the total quay length. Operationally, this prevents assigning a vessel partly beyond the physical quay wall, which would be impossible to execute. This constraint is part of the logic that prevents two vessels from occupying the same quay space at the same time. Operationally, it ensures that if two vessels are simultaneously in service, their spatial intervals along the quay do not overlap. This is what turns berth allocation into a two-dimensional problem: space and time. This slide continues the non-overlap logic. It provides the complementary condition needed so the model can consistently choose an ordering of vessels along the quay when both are present. Operationally, the two non-overlap constraints together ensure that any pair of overlapping in time vessels is placed in a physically consistent left-to-right order along the quay. This constraint enforces that service cannot start before arrival. Operationally, it prevents the schedule from relying on impossible early starts. It also makes waiting time visible. If the berth is not available, start time must be later than arrival time. This constraint defines finish time as start time plus service time, where service time depends on workload divided by effective productivity. Effective productivity increases with more cranes but is reduced by interference. This captures a critical reality. Adding more cranes does not always scale linearly. Past a point, cranes working too close slow each other down, so you must balance crane count against interference. This constraint limits each crane so it is not assigned to more than one vessel at the same time. Operationally, it prevents double booking. A crane is a physical resource that can only work one vessel at a time, and crane scheduling must respect that. This constraint ensures that every berthed vessel receives at least one crane. Operationally, without at least one crane, a vessel cannot be processed, so the schedule would stall. This is a feasibility requirement. This constraint enforces that cranes assigned to a vessel are contiguous, meaning no gaps. Operationally, this reflects physical crane mobility constraints and safety rules. Cranes cannot cross each other, and assignments with gaps can be infeasible because they imply cranes jumping over one another or leaving unreachable positions. This slide visualizes the integrated nature of the problem. Spatial berth allocation along the quay combined with temporal crane assignment. Use the figure to connect the math to operations. The berth plan determines which cranes can physically reach which vessel, and the crane plan determines how fast each vessel can be completed, which then changes berth availability for the next arrivals. This example includes 3 vessels. Vessel 1 is 300 meters long with workload 800, arriving at 800. Vessel 2 is 300 meters long with workload 1,200, arriving at 1,000. Vessel 3 is 200 meters long with workload 400, arriving at 1,200. Crane productivity is 30 units per hour per crane, and the interference factor is 0.1. The example assigns Vessel 1 3 cranes, Vessel 2 3 cranes, and Vessel 3 2 cranes. The resulting service times are 11.1 hours, 16.7 hours, and 7.4 hours. The key lesson is that crane assignment and interference directly change service time, which then changes berth congestion. Tier 2 uses a constructive heuristic. Decide a processing sequence using a priority rule, then assign berths and cranes using best fit logic. The value is speed. Instead of solving a full mixed integer model, the heuristic makes reasonable decisions quickly, which is often necessary in daily planning. This flowchart shows the two-phase process: compute priorities, order vessels, then assign berth position, start time, and crane count iteratively. Operationally, the algorithm must continuously check feasibility, available quay space, available cranes, and the effect of assigning cranes on completion time. In the first code section, the heuristic typically computes priority scores from vessel workload, vessel size, and time pressure. The practical idea is to identify which vessels create the highest delay risk per unit of capacity, then process them earlier when resources are tight. This section usually performs the assignment. For each vessel in priority order, choose the best berth position and a feasible crane count. Operationally, this is where the integration appears. If cranes are scarce, you may berth a vessel but give it fewer cranes, increasing service time. That longer service time can block quay space, so the heuristic must manage that feedback. This slide reports a specific heuristic output. The priorities are computed as Vessel 1 priority 0.33, Vessel 2 priority 0.67, and Vessel 3 priority 0.50. The sequence becomes Vessel 2, then Vessel 3, then Vessel 1. The heuristic assigns vessel 2 at position 0, starting at 1000, with 3 cranes finishing at 240 the next day. Vessel 3 is at position 300, starting at 1200 with 2 cranes, finishing at 1924. Vessel 1 starts at 240 the next day with 3 cranes, finishing at 1347 the next day. The heuristic is reported to achieve 95% of optimal performance. Tier 3 applies particle swarm optimization to search for better integrated schedules than the constructive heuristic. Each particle represents a complete solution encoding berthing positions, start times, and crane allocations for all vessels. The swarm updates solutions using personal best and global best memory, enabling exploration of complex trade-offs between berth utilization and crane productivity. This slide visualizes how particles move through the solution space. Operationally, think of each move as a coordinated adjustment, shifting a vessel slightly along the quay, delaying a start time to avoid conflicts, or changing crane counts to shorten service time while controlling interference. This section typically initializes particles, velocities, and evaluates fitness. Operationally, fitness must reflect the objective: total turnaround cost plus penalties for any berth overlaps or crane feasibility violations. This part updates velocities and positions based on inertia, personal best, and global best influences. The key is balancing exploration and exploitation. Too much exploration creates noisy schedules. Too little exploration can trap the swarm in a poor local solution. This section usually handles constraint repair or penalty evaluation. Operationally, integrated berth and crane schedules have many hard constraints. If a particle proposes a schedule that overlaps vessels or double books cranes, it must be fixed or strongly penalized. This part typically repeats the evaluation loop and updates best solutions. Over iterations, the swarm should converge toward a stable integrated plan with lower cost and fewer conflicts. This slide reports a PSO result with 50 particles and 200 iterations, using inertia weight 0.7 and both learning parameters equal to 1.5. The best solution found assigns vessel 1 at position 0, starting at 8:30 with 3 cranes and total time 20.1 hours. Vessel 2 is at position 300, starting at 1000 with 4 cranes and total time 18.7 hours. Vessel 3 is at position 600, starting at 12:15 with 2 cranes and total time 7.65 hours. The method achieves 97.8% of optimal quality with convergence after 147 iterations. Tier 4 treats berth and crane allocation as sequential decision-making. At each step, an agent chooses which vessel to assign, where to berth it, and how many cranes to allocate. A dueling deep queue network architecture helps the agent learn which states are valuable and which actions are best. The intent is to learn policies that generalize across varying arrival patterns, rather than solving each instance from scratch. This slide defines the reward structure in words: penalize waiting time and service time, and reward good utilization. Operationally, the reward must push the agent to reduce queues while keeping cranes and berth space productive. If utilization is ignored, the agent can produce low waiting for a few vessels but waste capacity overall. This slide shows the dueling deep queue network architecture used for learning. Operationally, dueling architectures can help learning stability because they separate learning the value of being in a state from learning the advantage of taking a specific action. In the first pseudocode part, you typically define the environment state, action encoding, and initialize the network. Operationally, action feasibility is critical. The agent must respect berth length limits, non-overlap, crane availability, and contiguity. Infeasible actions should be masked or penalized. This section usually defines experience collection and replay. Operationally, replay improves sample efficiency and stabilizes training, which matters because disruptions and rare congestion regimes must still be learned. This section typically contains the update step where the network is trained on sampled transitions. Operationally, stable updates are needed so the learned policy does not oscillate between over-allocating cranes and starving other vessels. This section often covers target network updates and exploration strategy. Operationally, exploration must be controlled in deployment. Training is done in simulation, but the deployed policy should be stable and conservative around hard constraints. This part typically logs performance and checks convergence. Operationally, convergence means the policy's decisions become consistently good across many simulated weeks, not just one scenario. This section often includes evaluation against baseline rules. The goal is to verify that learning actually improves outcomes beyond a rule-based heuristic. This final part usually extracts the final policy and prepares it for deployment. Operationally, deployment requires monitoring for drift and maintaining a fallback plan when conditions change beyond training. This slide reports training results after 5,000 episodes using historical vessel arrival patterns. Average vessel turnaround time is 18.3 hours versus 21.7 baseline. Berth utilization is 87.4% versus 79.2 baseline. Crane utilization is 82.1% versus 75.8 baseline. Convergence occurs around episode 3,200. The approach achieves a 15.7% improvement over rule-based heuristics. Tier 5 uses a digital twin to integrate vessel traffic simulation, berth infrastructure, crane dynamics, yard operations, and external logistics signals. Real-time data includes AIS vessel tracking, Internet of Things sensors, and weather forecasting. Rolling horizon optimization replans over 24 to 48-hour windows and triggers re-optimization when disruptions occur. This slide presents a system-of-systems simulation with predictive analytics and optimization loops. Operationally, it supports what-if analysis and fast replanning when cranes fail, vessels arrive early or late, or weather reduces handling productivity. This slide reports results over a 48-hour period. The twin processes 23 vessel arrivals, 15 crane status changes, and 127 weather updates. Reported performance includes 94.7% berth utilization versus 87.2% under static planning. Average turnaround time is reduced by 12.3%. Schedule adherence reaches 97.1% despite 18 disruption events. Operational performance includes less than 200 milliseconds data latency and a 4.7-minute optimization cycle. Tier 7 uses a Centaur model combining Sarah Chen's strategic judgment with artificial intelligence optimization and pattern recognition. The system provides recommendations with explanations, confidence scores, and alternatives. Humans can override based on customer relationships, weather contingencies, labor, and maintenance windows. The system learns from interventions to reduce future blind spots. This slide summarizes the architecture, explainable recommendations, oversight, and continuous learning from feedback. Operationally, it formalizes how human and artificial intelligence roles interact in high-stakes decision-making. This slide reports a 72-hour scenario with 15 vessels. The system provides confidence levels such as 87% for high-priority cases and 64% for complex assignments. Human adjustments include prioritizing a premium customer vessel at an added cost of 3.2% to protect relationships. Reported outcomes are average turnaround time 16.8 hours versus 18.1 for pure artificial intelligence and 21.4 for human-only planning. Customer satisfaction reaches 94.3%, and berth utilization is 91.7%. Tier 9 introduces quantum annealing as a way to tackle the combinatorial explosion of integrated berth and crane decisions. The problem is reformulated as a quadratic, unconstrained binary optimization model, where penalty terms enforce constraints. The quantum solver performs a global search and can also provide strong starting points for classical refinement. This slide defines binary variables for assigning a vessel to a berth position and start time, and for assigning cranes. Operationally, the point is to encode discrete decisions into binary form so they can be optimized in a quantum annealing framework. This slide describes the objective terms of the quadratic unconstrained binary optimization expression. Operationally, objective terms represent cost drivers such as delay cost, service time cost, or penalties for inefficient utilization.